In the last lecture we discussed about the time history. Once I have the stress range time history available to me, based on which I can use what we call the rain flow counting technique to find out the fatigue damage of each stress group and successfully the cumulative fatigue damage. Okay. In this lecture we will talk about deterministic fatigue damage using some spectral approach. Deterministic fatigue analysis methods actually apply the minus rule. Loading on the structure is represented by the loading cases varying from 1 to g, as we saw in the last example. Each cycle will be defined with ng, which is called number of cycles in time t. The structure is analyzed to determine the stress group Sg of each group and the total damage is estimated in a given time t. If the value of time t chosen to be 1 year, then the fatigue life is simply 1 by the damage of per year. When the fatigue damage is high, majority of the damage occurs on low cycle end of the curve, where the slope of the curve is typically 3 for marine structures materials. When the structure is under dynamic loading, the structure is then excited near to its natural frequency. In that case, the small changes in assumed period of the load can affect the result significantly, because it will start resonating. So, all your examples, all your case studies, what you did when the structure is subject to dynamic loading and the frequency matches with the natural frequency of the system, then your method of estimating the fatigue damage based on stress cycle count will be wrong. So, marine structures under wind and waves act as a period dependent filters. That is a very important property, because this property actually comes from the virtual design of a marine system, because we design a floating structure, we design a deep water draft platforms. So, they filter certain frequencies, okay, they allow only certain frequencies. As a virtue of the design, they magnify certain periods and suppress some of them. Okay. So, this is essentially achieved by the structural form and design what you follow in marine structures. As a result, the number of cycles of stress response may differ from that of number of loading cycles. That is very important, because you are suppressing the loading system on certain frequency domains or certain period domains. So, this difficulty can be handled in what we call spectral analysis, because once you started playing with the selection of time domain where your structure is operating, and at that range you want to look at the fatigue damage, then obviously you cannot do it with the time series of stress cycle ranges. You should look for the spectral analysis. So, let us talk about deterministic fatigue analysis. It is performed using semi empirical relationship. When the structures are subjected to waves, only one wave analysis is used to describe the lifetime stress history of the structure, that is assumed. For long term exceedance to be a viable form, if you understand that the long term exceedance is of a viable distribution, then the stress which exceeds the range sigma, the number of that will be given by this expression as you see in the screen now, where n is the number of stress cycles exceeding sigma in n naught cycles. Sigma naught, what you see here in this equation, is the stress that is exceeded once in n naught cycles, which is known to you for a given problem, and h, what you see here, depends on the load and response characteristics of the structure. Essentially it differs, or the value lies between 0.5 to 1.5. Okay. So, this is an empirical relationship which is used when the long term exceedance of your stress range is of a viable distribution. If it is of a different form, let us say it is of a log linear distribution, these are the two common types of distribution which is considered for long term exceedance in marine structures. In that case, the equation what you see here is related to not the stress, but related to the wave height directly, where h naught, what you see here, is the wave height which is exceeded once in an n naught cycle, which is again a known parameter, and of course h, what you see here is the wave height which is exceeded n times in the n naught cycles. Okay, that n is here which you are finding out, and n naught is already known. The long term exceedance can be combined with a single slope of Sn curve to estimate the fatigue damage in n L cycles. Okay, if your Sn curve is having a single slope, m is a unique number. So, if you want to estimate the fatigue damage for single slope of SN curve where m is fixed, then if it is a variable distribution I can use this equation. dl is given by NL sigma naught to the power m, and this is a gamma function. The gamma function is evaluated using this equation, okay, and this is a natural logarithm of n naught m by h, where h is defined already. If it is log linear wave height exceedance, then use this equation for fatigue damage. If the slope of the SN curve is a single value, there also you have got the gamma function. In this case use the stress range, whereas here you use the h value, which is the wave height, okay. The gamma function in both these expressions is given by a simple equation like this. This is a standard function and the values of gamma function are available in the standard statistical tables. For our understanding, let us try to plot, or let us try to list some of the gamma function values which are available in all standard statistics books. Let us see how this can be evaluated. Gamma function, which is actually given by an expression 0 to infinity x of g minus 1 e minus x dx for various values of x. I should say is a standard function whose values are readily available in the table, but still let us try to write down this value. So, I should say an example of the gamma function. So, let us say for different values of x I am looking for gamma x. Two, 2.5, 3, 3.5, 4 and 4.5. The gamma functions, the values of these functions for different expressions available here are 1, 1.33, 2, 3.32. These are the values of the gamma function, respective values of the argument. 6, 11.6. Now, let us look at the spectral fatigue analysis. It is applicable to structures that are executed in the dynamic loading which has stationary properties for large number of stress cycles. For example, if you are looking for wind turbulence, wave load effects, etc., which are executed in dynamic loading format, then I must use what we call spectral fatigue analysis. The spectral method uses the shape of the stress spectrum to determine the number of stress cycles of various sizes, because the last example in the rain flow counting method, the shape of the stress spectrum was not counted. We only look at the peaks and valleys of the stress cycle and counted the cycles, number of cycles in the stress range, and found out the fatigue damage estimates, okay. This is not applicable when the structure is excited in a dynamic loading condition and unfortunately the frequency content of the loading matches with that of the natural frequency of the system, okay. So, I must use the spectral method, which should in fact use the shape of the stress spectrum itself to determine the number of stress cycles of various sizes. Sizes means stress ranges, okay. Now, the stress spectrum can be narrow banded or broad banded. Now, how a narrow band stress spectrum will look like and how a broad band will look like. Let us say this becomes my narrow band spectrum, where this is my frequency in hertz and this becomes my S sigma sigma, and this is my narrowband spectrum, and the corresponding time history can look like this. And so on. for a broadband f in hertz S sigma sigma, it have multiple peaks. In that case, look at the time history, this will vary very randomly. In fact, so obviously you cannot easily use a peak and valley counting for this, right, because the variation is very highly random. So this is what I call as narrow band spectrum and time history. This is broadband spectrum and time history. Now let us say my stress cycle range is a narrowband spectrum as you see here. If it is a narrowband spectrum, to perform fatigue calculation we must now compute 0th and second moment of the spectrum about the line where f is equal to 0. Okay, I must compute the 0th and second moment of the spectrum, which I call as M0 and M2. I will come to that. The stress spectrum is now plotted with the frequency in x axis in hertz as you see here. It is common to assume a Rayleigh distribution of the stress range for a given spectrum. M0 and M2 can be computed using numerical integration technique. M0 is the area under the spectrum which corresponds to variance of the signal. The mean zero crossing period is now given by the mean zero crossing period which I call as Tz, will be simply given by square root of M2 by M0, oh sorry, inverse of this M0 by M2. And the number of stress cycles which I call as n in time t seconds is given by simply T by Tz. The Tz is already known to me. Then the probability density function for Rayleigh distribution of the stress range, the probability density function of the stress range is given by sigma r, which is sigma r by 4 m0 e to the power of minus sigma r square by 8 m0. Therefore, in t seconds this t seconds can be typically 3 hours for a sea state. In marine structures can be 1 hour for wind loads. This is for sea state in terms of waves, can be 3 hours, it can be 1 hour for mean wind duration. So therefore, in t seconds the number of cycles or the number of stress cycles which I call as delta n in the band of delta sigma r, which is centered at sigma r, is given by delta n is n, the probability density function what you already had in the previous case, delta sigma. Call this as equation number 1. Now, the fatigue damage associated with that band of stress cycle, because even in rain flow counting also we tried to find out the damage for each range. Okay. So, here instead of saying range we are saying it is band, that is nothing but delta sigma r is the stress range, that is a small band of stress range. Okay. If it is narrow band we are discussing this. So, fatigue damage associated with that band of the stress range is given by delta d. I am using delta for the small band. So, which is nothing but delta n by n, delta already you know, we can substitute it here. Now, we already know n also, delta n by n is the standard equation for the SN curve, which is nothing but a sigma r minus n. Okay, I am using this range, which is the range of the band. Okay, equation 2. Now, I already know the expression for delta n, which is a function of probability density function of sigma r. Let us substitute back all of them and see that delta d can be now simply n of probability density function is sigma r by 4 m naught e to the power of minus sigma r square by 8 m naught of delta sigma r by a sigma r minus, calls equation number 3. Now, if the SN curve has a constant slope, then the above equation has a standard solution. For a constant slope. Let us write down that equation here. For a constant slope of SN curve, the solution turns out to be a standard gamma function, which is written here, 0 to infinity exponential minus b x to the power of c dx, which can be simply gamma function of a plus 1 by c divided by c b a plus 1 by c. I call this equation number 3, where we already know where gamma function of any value g is given by 0 to infinity x of g minus 1 e minus x dx. This is standard equation for evaluating the gamma function. Now let us compare this equation with our standard form and see what happens. Let us say delta D already I know is n sigma r by 4 m naught exponential minus sigma r square by 8 m naught delta sigma r by a sigma r minus m. This is the damage for a small narrow band of sigma r. I am looking for the cumulative damage, is it not? That is what we also did in the last example. So, the fatigue damage for all cycles is given by integrating the above equation. Let us integrate this. So, I must get d which should be integral of 0 to infinity, the same equation simply write here n sigma r by 4 m naught e to the power of minus sigma r square by 8 m naught delta sigma r okay 1 by by a sigma r minus m. Now, the argument is sigma r. Let us try to simplify this equation. Simplifying, we get, I am rewriting this, d can be said as n by 4 m naught, okay, n by 4 m naught, I take it out, integral of 0 to infinity so I have sigma r here, I have sigma r of minus m here, okay, I can say sigma r of m plus 1, okay, then exponential minus sigma r square by 8 m naught delta sigma r now let us compare this with the standard equation comparing with sorry not a m naught can be written as 4 a m 4 a m. Is that okay? Sigma r m plus 1 exponential sigma r square by 8 m naught. Okay. Now I compare this with the existing expression x power a exponential minus b x c dx. Okay, the argument is if it is x power a it is dx, if it is sigma r it is delta sigma r. Okay, the argument is similar, I can compare these two. When I compare, because this also integration from a limit, okay, I can straight away say a is m plus 1 isn't it? A is m plus 1 and B which is 1 by 8 m naught, because there is minus minus sigma or sig x. C can be different, but B is 1 by 8 m naught, 1 by 8 m naught, and C is 2. Okay. So, I can now evaluate this expression. It's a standard gamma function. Okay. That gamma function was given to you, that was gamma of a plus 1 by c by c b raised to the power of a plus 1 by c. Is that okay? Is that okay? So, now I can write this value as gamma function of a is 1 plus 1 m plus 1 by c is 2 by c is 2, b is 1 by 8 m naught raised to the power of m plus 2 by 2. Is that okay? I get this as m plus 2 by 2, which can be gamma of m plus 2 by 2 by okay. This can be evaluated like this. Hence, the total fatigue damage for n number of cycles d can be now said as n by 4 a m naught gamma of m plus 2 by 2 divided by 2 of 1 by 8 m naught of m plus 2 by 2. Simplifying, because I got m naught here, 2, 8, 4 etc. Simplifying them, I got a power also. Simplifying them, can say n by a, because this 4 and this 4 goes away. I will get 8 m naught m by 2 of gamma function m plus 2 by 2. That is my total damage. Is equation number 5. Now, I already know, we already know that n, what is n? Turn back and tell me what is n? N is number of cycles, which you can say T by T z, is it not? And what is T z? Square root of m naught by m2. Good. So, I have T z here, substitute here, I have n here, substitute here, I get D as T m2 by m naught, because this T z is the denominator, 8 m0 raised to the power of m by 2 by a gamma function of m plus 2 by 2. Is that okay? This becomes equation number 6. For a given slope, standard slope, okay, this is all for constant slope. For a constant slope of m, maybe 3, you already know it is going to be 2.5. Look at the table. For gamma 2.5, you already know the value of this function. Okay. So, if you know the spectral moments m0, m2 etc., m is the slope, okay, m0, m2 spectral moments, and you already know the value of t where you are evaluating the d, and A is again the constant of the SN curve. Okay. You can find the cumulative damage for a narrow spectrum of the stress cycle as you see from this expression number 6. Okay. Now, to calculate M, the spectral moments, the general expression is to calculate the spectral moments M naught is given by 0 to infinity S sigma sigma f df, and M2 is given by 0 to infinity S sigma sigma f square df, where I try to plot a spectrum. The frequency is in hertz and this becomes my stress and let us say S sigma sigma. The ordinate is nothing but stress square by unit frequency. So, if I get a specific spectrum like this, you want to look at a specific value, f is the distance while you are plotting here, this is f and this is x sigma sigma f. So, M0 and M2 are given by these two equations and gamma function is already known to you. For m is equal to 3, gamma of 2.5 from the table is 1.33. Okay, you know the gamma function here. So, the above equation what you see here gives the fatigue damage for duration of one particular spectrum. If we really want to calculate this for a long period, then this should be repeated. The steps should be repeated for all different spectra. Because you have got a specific spectra S eta. For all different spectra you will repeat this. That can occur in the marine structure. In that case T then becomes cumulative time for which each spectrum occurred. So, T is no more related to one specific value, it becomes a cumulative value. So, equation, what was the spectral damage equation lastly we had? The equation number? Equation 6 is widely used in fatigue damage estimates of marine structures. If it is a narrowband. Now, let us quickly compare this with a constant amplitude loading, because in this case stress cycle is varying, that is why we are plotting the stress cycle spectrum. Okay. If it is a constant amplitude damage, comparing this constant amplitude damage, we know that for a constant amplitude loading D, that is the damage, is given by n by n, is it not? We already know this equation, which is nothing but n by A S minus m, where n is the number of cycles and T is of course square root of m2 by m0. I want to compare this method of estimating damage for a constant amplitude with that of equation 7, that is what I am 6, that is what I am trying to do. So, instead of having a single simple amplitude of the stress, I will have an effective stress amplitude. Okay. So, the stress amplitude is replaced by effective fatigue stress range. Which is sigma EFR, effective fatigue stress range. Sigma EFR is given by 8 m0 to the power half, that is the equation what I am writing from equation 6, is it not? Gamma m plus 2 by 2 raised to the power of 1 by m, is that okay? Look at equation 6. Equation 6 I am writing for our understanding. Equation 6 was n by A 8 m0 raised to the power of m by 2 gamma m plus 2 by 2, is it not? Okay. I am comparing this, I am trying to find out what is the equivalency of effective fatigue stress range compared to the standard damage. I get this equation, equation number 7. So, this is what we call as effective fatigue stress range. You can also rewrite this effective fatigue stress range can also be expressed in terms of RMS values. So, sigma of RMS, that is root mean square of the stress range, is given by 2 of root of 2 m0. So, significant effective stress range, sigma significant can be 4 m naught. So, therefore, I can write sigma EFR as sigma RMS. 8 can be 4 into 2, that is 2 root m2, okay, half is already there, okay. So, I can say this is sigma RMS simply m plus 2 by 2 of 1 by m, or sigma effective R can also be said as sigma significant, which I know here, which is 4 m naught, which can be now gamma function of m plus 2 by 2 to the power of 1 by m by root. Is that okay? Because 8 is 2 root. Okay, I already have 2 here. So, I divide by root. So, I can write sigma effective fatigue stress range as this in terms of RMS or this in terms of significant, because from a given stress spectrum you will be getting these values. Sometimes you will get these values in the literature. Can find effective stress range. Once you know the effective stress range, I can easily find the fatigue damage as comparable to a single constant amplitude damage like this. Okay. Now, let us quickly look at the summary of this. So, for our understanding, let us plot a table for different values of m. M is nothing but the slope of the SN curve, okay, where I say sigma EFR by sigma RMS, sigma EFR by sigma significant for different values of m. So, for different values of m, I must know how to evaluate the gamma function for values of m. Gamma function equation already given to you, and you know the table also, okay. So, let us plot for the slope of the curve cannot be 0, okay, slope is having some value 1, 2, 3, 4, let us say for example. Can you give me the value of sigma EFR for 2, because 1 you may not have the value. So, if I substitute m is equal to 2 here, I get gamma function as at 2.5, which is 1.33, okay, 1.33 to the power of 1 by 2, that is root of 1.33, okay. So, sigma FR by sigma RMS will be that value. How much is that? Root of 1.33. So, this value is going to be 1.099 by root 2 and so on so forth. So, I can easily find out these values. Let us quickly write the summary. For a narrow band spectrum of stress cycle range, for a narrow band spectrum of stress cycle range, fatigue damage can be estimated as below. First, find out m0 and m2, because you need the spectral moments. m0 is nothing but 0 to infinity S sigma sigma f df, m2 S sigma sigma f f square df. Then find the mean zero crossing period, which is Tz, which is nothing but the ratio of m0 by m2. Is that okay? Is that right? Tz m0 by m2. The number of cycles in time t which is given by n t by t. Once I know this, I find effective constant amplitude. Which I call sigma EFR. Sigma EFR is given by 8 m naught to the power of 1 by 2 gamma function of m plus 2 by 2 to the power of 1 by m. Now select the SN curve. Select the SN curve defined by n is equal to a s minus. Now estimate the fatigue damage. D, which is given by sum of n by n which is nothing but sum of n sigma EFR, that is my stress, because instead of S I am going to use effective stress range which is going to be m divided by A, because actually n is A s power minus m, it goes up, becomes m, and S is sigma EFR. Sigma EFR is already known to me. Okay. So if I know m naught for a given spectrum which is given by this equation, and if I know the value slope of the curve m which is approximately 3, I can find sigma EFR. Sigma EFR is known to me, I can find the damage. In the next class we will talk about the broadband spectrum, because we discussed about narrowband spectrum here for a stress cycle range. If it is narrowband, I can easily handle this 7 steps, I will get the fatigue damage in years. If I have got a broadband, I will apply some corrections and convert that into a narrowband. Okay, that is what people have been doing to find out the fatigue estimates for broadband spectrums. Okay. Now in this lecture we understood that why at all we go for a spectral fatigue damage, why not a time series. In the last lecture we discussed about the time series estimates of fatigue damage simply by rain flow counting technique, where we understand only the peaks and valleys. In this case I cannot handle, because if it is a dynamic loading as in case of wave or wind, the response of the structure excited under this band of near resonance frequency will not clearly give you a correct picture of the damage. So I must look for a stress cycle spectrum. It can be narrow, it can be broad. If it is narrow, I know how to handle it. If it is broad, how to handle it. Next lecture we will discuss this. Thank you.